I'm Tim, and I'll talk about how we enable batch differentiation in enzyme today. So first of all, what is vector mode AD? We have the following use cases. We want to make optimal use of our hardware. That can be that's mainly the SIMD vector cores in our machine, and for that we can apply forward mode AD, which computes the derivative for all inputs. And we can also use reverse mode AD. We can vectorize that, which computes gradients with respect to multiple outputs. And we also have batching of primal code. So what are the benefits of vectorizing forward mode especially? The problem of vectorized forward mode AD, as we'll see later, is embarrassingly parallel. We can avoid the re-evaluation of our original function, e.g. the primal function. And we can also cache values from the original function like only once for like a whole batch of derivative evaluations. So here you can see how the evaluation of the derivative is embarrassingly parallel. So the control flow only depends on the primer, and we have no dependencies on our vectorized operators. And another benefit is that we can, if we were to have like a very expensive call, like our call to slow here, we can cache that once and reuse it for every successive forward mode evaluation, which we can see here. So slow is only evaluated once. And we can make use of vector mode in this case to basically simulate some kind of gradient evaluation here by encoding our parameter x, our vector x, using like a one-hot vector scheme, which I'll go into detail next. So here we can see how you would basically enable only one of the inputs to get to propagate that to your output variable, and this way you can get the derivative with respect to dx, dy, or dz, and this is how you would seed those values. And there are two variants to calculate Jacobians. You can use forward mode, which computes the vector Jacobian product column-wise. You can use vectorized reverse mode, which computes the Jacobian row-wise. For our implementation in enzyme, we need to know the vector width statically at compile time. So, yeah, okay. And the complexity in general for forward vector mode depends on the number of outputs and the batch size, and for reverse mode, it depends on the output and related to the batch size. So here's the vector Jacobian product, as I already said. This computes the Jacobian column-wise. So we again seed our input gradients, not grades, derivatives one-hot wise, so that we propagate the correct derivative to the output. And on the side is like an example for how you would do that in Julia using enzyme.jl. And here we can see how we can compute the vector Jacobian product. And this time we have to seed our outputs in a one-hot encoding, so that we can propagate the correct gradients to our inputs. And yeah, down there you can see how this is computed row-wise instead of column-wise. And yeah, both are equivalent in the end. And now let's talk a bit about the design. First of all, we perform activity analysis in enzyme. That we do in order to determine which instructions are active and which instructions are not active. So that means some instructions are not like relevant to our derivative computations, and we just discard those in the derivative computation. And this is just as we do it in like scalar normal mode. And in some cases, we also need to perform type analysis. We'll go into detail why that might happen later. But this is not always required for forward vector mode. Next, we generate code where we propagate each active value with its derivative through our computation graph. And we also make sure to have shadow pointers for all our pointers and also have allocations for those on the heap, if necessary. And then we emit all those instructions. Like for the way we vectorize a function is we emit like a bunch of scalar instructions, and we then rely on the LVM vectorizer to do the rest for us. So that would be the SLP vectorizer who would do the heavy lifting. We've also looked into other approaches where we would emit loops or even emit LVM vector instructions. But this one is the most stable as of now, and that's what we currently use. So when we want to vectorize LVM types, we have a problem that is related to the array of structs versus struct of arrays problem. So if we imagine we have like a point here which has an x, y, and z coordinate, and we want to vectorize that, there are two ways we can do that. First, we can just create a struct that has an array for each field, which would then be array of structs. And then we have a second possibility, which would be struct of arrays, which then would just basically have an array of our original point struct. And those approaches have different drawbacks, but in general, array of structs is preferable. And even that can be improved upon if you make it like cache line aware. But we are not doing that yet in Enzyme. And yeah, the one case where struct of arrays is better is when you just work on multiple like points at the same time instead of working on like multiple like instances of like x at the same time. But that rarely happens. So those two ways of vectorizing the data types translate to what we call an enzyme vectorization of the root node, which is array of structs, and vectorization of leaf nodes, which relates to struct of arrays. And the first one gives us a better compatibility because you guys don't need to rewrite your data structures. You can just pass your struct to Enzyme, and Enzyme can just like duplicate the struct n times. And for the second mode, you guys would need to rewrite your struct and have that be vectorized, which yeah, is not always nice to do. Here is how an LVM type would look like. And I drew this as some kind of tree, so you guys can see where the leaf nodes are. And so for our first approach, vectorized at the root nodes, we can just basically, if we want to vectorize by 2, we can just plug that into an array and be done with it. And for the vectorization at the leaf nodes, it gets a bit more complicated, where we just have to consider each leaf node value and vectorize that by 2. Note that we stop at pointer boundaries and then just apply this whole scheme recursively, so that we always only have one pointer instead of n. We never have n pointers. All right. There are also a few optimizations that can be applied to vectorized AD. The activity analysis, which we already talked about, prevents propagation of values we don't need, which are inactive. And we can also combine calls to allocation and respectively to free calls. And here are some kind of benchmarks we ran. So the red one is just the forward vector mode, vectorized at the root node. The purple one is vectorized at the leaf node. And the last one, the green one, is tapenade for reference. And you can basically see that expectedly the leaf node approach scales way better than the root node mode, and yeah, we have the best of performance just around the SIMD vector width of our actual machine. So, or yeah, just around that. So that kind of depends. Yeah, and the main bottleneck we will run into here. So at this point, we do not effectively use our whole machine. So like the SIMD units are not properly used. And here we run into a lot of register pressure. That's why we lose scaling over there. And yeah, this has also been done for the Rosenbrock benchmark and for LSTM, where scaling behaves quite nicely. Yeah. Are there any questions? Okay.
So in a way, this is a bit reminiscent of Jux VMAP, right? So vectorizing all your code. Can you also just vectorize Python code that you don't want to differentiate through?
Yeah.
Right.
So I maybe didn't really, no, I didn't mention that. Yeah, I was supposed to mention that. We also have something like VMAP, which can, like, in a very simple way.
And can you VMAP VMAP?
No.
Okay.
I haven't tested, but I wouldn't think so.
Okay.
Maybe. But yeah, that's very crude right now, but you can feel free to try it out.
Then maybe one a third question. So you talked about those two flavors of where to put the additional access. Could you briefly say how easy it is to configure that? Because I think in terms of my kind of problems that we tackle, and we usually have a lot of FFTs into our models, and for us it would make a lot more sense to have what you would call to have an array of points instead of points of arrays.
Mm. Yeah, so configuration-wise, if you're just passing arrays, that is pretty simple. On the Enzyme side, it basically makes no difference for the two modes. It just becomes complicated if you have deeper data structures like, yeah, structs, basically. And yeah, that you can, basically we have an interface where you can just pass an offset, so you can tell Enzyme how long one data structure is, and it'll just know from your buffer where everything should be put in place.
Any other question?
For the tapenade reference point, did you just use vanilla tapenade or the version that generates SIMD-ized vector loops?
I think that was vanilla. I used the website to compile that.
But we used the version from, like for the actual benchmark, I think we used the version from ADBench though, so that should have, I think that for, at least for the LSTMs and GMM benchmark, that's definitely the version that's used for the generation of the ADBench numbers as well. I'm not entirely sure if that's, if they used the vanilla or the SIMD special version.
Other questions? Comments?